So you're just going to need that handout to follow along, but I started with a few pictures just so we could get an idea of what the size of an atom is. Okay? So you guys all know the size of a speck of a dust. It's halfway between the size of an atom and the Earth. Okay? The speck of dust is half the size between the Earth and the size of an atom. Okay? So that's telling you how small atoms really are, right? And so just looking at where we've been and how far we've come, we started with Dalton in 1803. Just that atom was just a solid piece of particle, right? Then we moved into Thomson in 1904, about 100 years later, knowing that there was positive and negative charges. He called it the plum pudding model. Then Rutherford with his nucleus in the center, right? He's the one with the gold foil that he shot alpha particles at. Then Bohr, that's 1913. He started seeing energy levels that are quantized. And Einstein and Planck and Heisenberg and which other one did you guys do? De Broglie yesterday, right? So there's other people, and we even talked about other people that brought about ideas of the atom throughout the years. So, funny little joke for you to read before we really get started. No, I'm not reading it. Oh, electron, it's proton, where are you? Ooh, that's tough, yeah, well, I can tell you where I probably am. Does that help? Okay. If you learned about Schrodinger and the probability of the electron being in that orbital or that area of a cloud, if you remember that from our little bit of a discussion, that's where that joke comes from. Or that's where the background of the joke is there. If you haven't got it yet, maybe I'll show you later on and it'll come back and you'll be like, I gotcha. Okay? So, there is fill in the blanks as we go through, and we're going to take it slow, reading through it. So, we're moving from the Bohr model to the actual quantum mechanic model, the charged cloud kind of model. So, Bohr's model for hydrogen was based partly on classical mechanics, the laws of motion that apply to objects on Earth and in the solar system. Bohr used laws of classical mechanics to calculate the possible orbits and speed of the electron in the hydrogen atom. Okay? It works for the hydrogen atom. However, he could not predict any more electron orbits using his model. So it only worked for hydrogen. Well, if it only works for one thing, and you see how many periodic table of elements, you see all the elements on there? If it only works for one of them, it's probably not the case, right? So they had to figure out something else. So quantum mechanics are now used to explain that the orbits are quantized, okay? They're of specific energy. And you guys saw some of this yesterday when you were doing your research, the fact that the light only bounced to a certain level, right? Or it got excited to this height or amount of energy. So orbits are quantized of a specific energy, and that the electrons jumped. It didn't change smoothly and continuously, as in classical mechanics, between orbits if the amount of energy is present. In modern quantum mechanical model, so the charged cloud model. So all the stuff that you were looking into yesterday, the quantum mechanics stuff, that's the charged cloud model that you're looking into. There's no orbits, okay? You cannot say it is an orbit. There's no path of the electron. Okay? It's just the probability of finding an electron in a certain region around the nucleus, right? So the big thing is that there is an area, an orbital in which these electrons will be found. The regions of highest probability for each energy level is a plot of points. The average position of these points is a shell or a cloud centered around the nucleus. The shell or energy level is the average of the points indicating the probability that the electron will be there at any given time. There's no path, okay? Electrons can go anywhere. Have you guys seen Miss Crafting's bulletin board in her room, where she showed the word success and they had an arrow, like straight and narrow, like there's only one path to success, but success doesn't look like that. Usually it's all over the way and you're taking all these different paths to get there. Her board or her diagram up there of going from work to success really reminds me of the path of an electron, because there really is no path. There's really no way to success. It's just you got to figure it out and you go all over trying to work hard and get there, right? So that's the same thing. Now, the highest region is a shell around. This shell or energy level is the average of the points indicating the probability that the electron will be there at any given time. These energy levels are called principal energy levels. The number assigned to each principal energy level is 1, 2, 3, 4, 5, 6. It's called the principal quantum number, or N. Okay? So our energy levels, if we're going to look off of a periodic table, match up with the rows, just so we know. Okay? So hydrogen and helium, which is on row 1, are in principal energy level number 1. Lithium, beryllium, boron, carbon, nitrogen, all those ones, what energy level do you think they're in? 2. Okay? So if I ask you, what is the principal energy level that calcium is in? 4, because it's in the 4th row. Are we good? Does anyone need me to stay here to finish this note? Okay. Are we good? Can I move forward? So, energy sublevels. So inside of the principal energy level, inside the principal energy level, there are things called sublevels. Okay? According to quantum mechanics, every atom has principal energy levels, and every principal energy level has one or more sublevels. Okay? Within it. Each sublevel has slightly different energy, and the Bohr's model didn't include the sublevels. That's where he went wrong. Okay? So he missed out on the sublevels. The number of sublevels in any principal level is the same as n. So that means in the first energy level, principal energy level, there's only one sublevel. It has the sublevel S, which we saw pictures of before in our other slide, the sphere, right? In the second principal energy level, it has 2 sublevels, which is S and P, okay? And the third, it has 3, S, P, and D, okay? Now, where are those located in accordance to the periodic table? And I think you guys have a little bit of room at the very bottom of your page. We're only going to really look at S, P's, and D's, so that's all you really need to know. But it goes S, P, D, F, and dot, 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 G, H, blah, 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 blah. But we really are only concerned with the S, P's, D's. but you can look at the F's as well. What does my diagram represent? Does anyone know what that is? Oh, good. I'm going to bring it up for the ones that are in the back. Maybe. Okay. That's the periodic table. So any electron that is in the S, where does that really match up with? Column 1 and 2, right? So that's column 1 and 2. I know it's not a perfect periodic table because I didn't bump down after hydrogen and stuff like that, okay? It's okay. The first two columns are the S sublevels, suborbitals. Then, if you jump over 13 to 18, those are your P's. Your D's are transition metals, and I will probably never ask you this, but your F's are down in your lanthanoid and actinoid kind of series down there, okay? Now, we've always had this issue with hydrogen as, what do we call hydrogen? The black sheep, because it's sitting on the wrong side. But why do we make hydrogen sit way over there? Why does hydrogen sit with that first column, but it doesn't have any properties like that first column? Because it has one valence electron. That's why it sits there. It has one valence electron. What's different about helium? What's different about helium and any of the other noble gases? Its full valence shell has 2. Okay? What do full valence shell normally have? 8. And you guys always said, well, some of them have more than 8. And this is going to explain, I always just said, it has 8, it has 8. We only count the ones from 1 and 2, and what else did I say? 13 to 18. Those are the ones we count as valence shells, right? Do you guys remember me yelling at you for that? No? We only count 8 valence shells. Why? Because the valence shells are the S's and P's. Okay, and I'm going to do more explaining on why they are the valence. Because what does the word valence mean? Outer, right? So the valence means the outer shell. So as we go on here, you're going to see reasons why we call the S and P suborbitals are valence shells of the electrons, of any atom. Okay? So, the lowest sublevel in any principal level is S. Okay? So you have 1s, 2s, 3s. Those are the first sublevels every time you list a principal level. So the first sublevel I will list is the S sublevels. Then comes the P's. And then after that comes the D's. Okay? It seems out of order because you're like, the D's are in the middle. But I'm going to show you something with those D's. Okay? So the first energy principal level, or N equals 1. 2s, N equals 2. 3s, N equals 3. What does N stand for again? Principal level. How many sublevels are in principal level number 4? Good. How many sublevels are in principal level number 4? 4. How many sublevels are in principal level number 2? How many sublevels are in principal level 5? 5. Your number of sublevels match the actual principal level. Okay? I don't. Okay. So, you guys have a big blank, do you not? You have this. Oh, you're lucky. I must have inserted it after. Okay. So, can I just go through this? Did you go through spectrums and stuff yesterday when you were looking at things, or things that went up by levels, right? This is the energy level as you go up. For the first 4 things that we've got. So the energy level for 1s1, so the ones in the first two columns, or in this case hydrogen and helium because they're the special guys, are right down here. They have the lowest energy level, and they're actually the closest to the nucleus. Principal energy level 2 is right here, right? 2s is lower energy than 2p. Okay? Principal energy level 3 is right here. 3s, 3p. But then notice what happens to 3d. 3d's energy is higher than 4s's. Okay? So that sublevel goes after for energy of 4s. Okay? So when we write things in sublevels and principal levels, we write them in order in which they appear. But I just want you to see this so you can see why column 3, like you look at row 3, not column 3, look at row 3, we have 3s, and then we have 3p, right, because it's over here, and then we go down and we're in column 4, or row 4, so that's principal level 4. But then all those ones from Scandinavium all the way to zinc, all those ones, those are actually level 3 things, okay? So we have to be cautious that, sorry, I got too far from that thing. It's like a little dog collar. I have to be close enough for it to hear me. When we look at it, those middle transition elements, they're just bumped down. So the transition metals that are in row 4 are really 3Ds because they appear just higher energy, than the 4s's. Okay? So even though I said the rows of your periodic table match up with your principal energy level, it's not quite right. Okay? But it does generally follow that pattern. 1s is there, 2s, 2p, 3s, 3p, but then we do 4s and then the 3ds, and then it's back to 4p's. Okay? And it carries on. If we had energy level 5, you'll notice that the D's, the 5s would actually appear right after the 4p's. This is where 5s's energy level would be. Okay? Just so you know. Is that okay? Are we happy with this? Quantize. So when n equals 4, there's a 4 sublevel F, G, and H, but in figure 3, there's some overlapping. I really want you guys to notice the fact that that's why the periodic table doesn't actually match up with their sublevels, is because there's more energy in 3D than there is in 4S. There's overlapping because 3Ds have more energy than a 4S. Okay? Can we go back to valence then? Did you guys see why we only have 8 valence electrons? Because those D levels and those F levels are up inside of some other main level, principal level. So the outermost levels, your outermost principal, the highest ones of them, before they jump into the next level, are your S's and your P's. And there's 8 of them. Well, you can fit 2, because it's 2 columns, 2 in S and 6 in P. So we're going to move into what the orbitals are actually called. So we have principal energy levels, we have sublevels, okay, and now we have orbitals. Okay? And don't ever write the word orbits in quantum mechanics theory. They're not orbits. They don't travel a path. They don't go around the nucleus like the Simpson model that we all know and love, right? They don't travel in those orbits. And I'm even surprised that the Simpsons used that because we already had the charged cloud model by the time the Simpsons rolled in. Probably just harder to draw. So, how do you figure out how many orbitals you have? It really depends on what sublevel is in each section. So as we went up, we gained a sublevel, so we actually gain spots to carry electrons. So no matter what principal energy level it is, you can figure out how many sublevels they have by going n squared. Not sublevels, sorry. You can figure out how many orbitals they have by going n squared. So orbitals, just so you know, are spots for electrons, basically. Okay? Places for electrons are the orbitals. Okay? Now, 1 squared means 1 orbital. Okay? Each orbital can hold 2 electrons, just so you know. 2 squared means 4 orbitals. 3 squared, or principal energy level 3, 3 squared has 9 orbitals, so places for 18 electrons. So if it asks you how many orbitals are in this principal level, you take that principal level and square it. And this is kind of nice to make note, just in the bottom here. Every S sublevel has one orbital. Every P has 3 orbitals, every D's have 5 orbitals, and every F's have 7 orbitals. Okay? Another way of remembering that is basically you double the amount. So you divide it by half. So you'll notice the S's, there's 2 columns, so I divide by 2, that's 1 orbital. P's, there's 6 columns, so divide it in half, so that means 3 orbitals. If you count across the transition metals, there's 10 of them. Okay? 10 of them divided by 2 gives me 5 orbitals. And then the F's, like I said, are way down at the bottom. If you count across there, there's 14 of them. 14 rows across there, or columns across, so 14 divided by 2 is 7. Ready? So now we know how many orbitals are in each kind of sublevel. So just like I was saying before, every single orbital can contain 2 electrons. So if you have 1 orbital, you have 2 electrons. If you have 2 orbitals, you can have 4 electrons. but depending on which energy level. So principal energy level 1, we can have one sublevel, which means 1 squared, so we have 1 orbital, and then 2 times 1 squared gives us 2 electrons. This equation, if you don't need to know the number of orbitals and you just want to know how many electrons you can hold in that principal energy level, you can put it in there. So in principal energy level 2, and we know we have 2s and 2 p's, right? Those are electrons. It's E with a little dash. The dash meaning a negative sign. So this is like behind that. 2 electrons. 8 electrons. Okay? And basically, if you want to know how many electrons are in each principal energy level, you can use that formula of 2n squared. Okay? Now, if you don't want to use that formula, you can remember the pattern from the periodic table and just count the number of electrons, right? So if you take a look on your periodic table, sorry, it's really bad drawing, but it looks like this, right? There's 2 columns here, then there's 10 columns in here, and then there's 6 columns this way, right? So realistically, in the first row, you have 1, 2, so you have 2 electrons. In the second row, you have 8, because you have 1, 2 plus 6 gives me 8. But on the third row, you have to remember that the D level sublevel is down in column 4, or row 4. So you have 1, 2 plus 6 is 8, plus these 10 that are down here. So you have 18 in principal level 3. So some people prefer to remember this formula because then they don't have to remember that 3D comes after 4S at this moment in time. Is that okay? All right. So I'm going to go on. Can I move on? So this is just a review. The number of energy levels, or your principal energies, are there. You could even talk about the number of sublevels per energy level. It just kind of gives you quick little formulas for all of them. Okay, so if you need those formulas, you can have them. We only have about one more section before I give you some questions here to work on, and that's talking about the shapes of the orbitals, which you already know, because I've told you that already this year. But let's just write it down so you have it somewhere, right? So, shapes of orbitals. Plots of charged clouds can be revealed to the different shapes. So all S's are spherical. They actually look like this one right here. The big difference between 1s and 2s and 3s and 4s is the fact that as you increase in principal energy level, you increase in size of the sphere. Okay? So as you go up in energy level, the actual size of the orbital gets bigger because you're getting further away from the nucleus. Okay? P are the next 3. Sometimes we call them PX, PY, and PZ because they're on a 3D plane. So you have up, down, side to side, and out and back. Okay? So you have an X, Y, and Z. I think P's are named after their shape. Peanuts, propellers I used, right? Some people call them dumbbells, but that doesn't make sense for me because like that doesn't help me memorize what the P shape is. Okay, but they do look like dumbbells in some cases. They just get shaped. So you have an orbital, one orbital this way, one orbital this way, and one orbital in and out. Okay? That makes 3 orbitals. Inside of each of those orbitals, there's 2 electrons. So you have 2 plus 2 plus 2, so 6 electrons in total. Then your Ds, you have 5 different shapes of Ds. But I'm not going to lie. I'm not going to ask you to memorize the 5 different shapes of Ds. Okay? But I do expect you to know that S's are spheres, and they grow larger as you go out in the principal energy level, and P's are propeller shape, and they also get larger as you go through the principal energy levels. Okay? Now, if you flip your page, right now we're at a section in your booklet that you have questions. Okay? This is what I want you to complete in the next 20 minutes. They're going to be marked. You're going to hand them in. Now, can I tell you one more thing? I'm going to flip this slide because the next thing is a really big copying thing. So in the next 20 minutes, not only are you finishing these questions, you can do it in the booklet or on a piece of loose leaf and hand it in. I also want you to draw the next diagram. Okay? So here's the next diagram. Well, it's questions or question set 1, and then I would use the title of the actual handout. Okay? So